Okay, well, thank you all for coming here this morning. This is a continuing installment in the Dean's Distinguished Lecture Series. And today we're very honored to have Professor Subhash Mahajan from Arizona State University. He's a Regents Professor, a very distinguished title at the University of Arizona. He is also an alumnus of the University of California from Berkeley years ago. He got his undergraduate degree in Indian Institute of Technology in Bangalore, and then went to Berkeley for his graduate degrees. He is an internationally recognized expert for his research on structural property relations and functional materials and deformation behavior of solids, which I think he'll tell us a little about today. He's also a very prestigious member of the National Academy of Engineering and coordinates editorship on 4 journals, if I'm correct, which keeps him busy in his spare time. So today he's going to speak on self-assembly nanostructures mixed in 3-5 and 3-N layers and their influences on devices. So with that, I'll turn you over to our distinguished guest. Please join me in welcoming Professor Mahajan.
Thank you very much for hosting my visit and the lecture. And it is my pleasure to come back to the region where I started my career in this country after leaving India. And what I am going to ask you, how many of you have seen the movie Graduate? It came in 64, 65 time frame. Some of you were not even born. And if you recall, Dustin Hoffman finishes his undergraduate at Yale and goes to Los Angeles to meet with his future prospective father-in-law. And they are at a swimming pool party, and the father-in-law says, plastics. And the same thing happened. I had no father-in-law at Bell Labs, but when I joined Bell Labs, my advisor or my department chair was Jack Wernick. He's no longer living. And he said, semiconductors. I told him that I can barely spell metallurgy, and you are asking me to work on semiconductors. He said, you will realize how important these materials are. So I am going to share with you my love affair with the semiconductors over the past decade, not decade actually, 3 decades. So what I've decided to talk about is what happens in these materials, 3,5 like gallium arsenide or mixed like indium gallium arsenide or aluminum gallium arsenide. And then is the current and is the nitrides. Nitrides are fascinating materials, and they have tremendous applications in number of devices and all that. What I will talk about is how the material science can interface with electrical engineering and solid-state materials and work as a team to solve difficult problems. And I'm associated, you may see the word schools, because there are 5 schools in Ira A Fulton School of Engineering. I'm in the dean's office now, and see what. Now, give you a flavor of the applications of these materials or where they're used. First thing is the major application is in the light wave communication of these 3-5. Yeah, this is better. Look at the indium phosphide. We didn't create these materials, they exist in nature. And you can change the band gap of these indium phosphide the materials when you mix with gallium arsenide. The beauty is they remain lattice matched to this underlying substrate. So you can make light emission devices which will emit at 1.33 or 1.55. You can make detectors in these materials which will absorb at 1.55 and still lattice matched. And these devices are used in light wave communication. You have a detector on one end, you have a generator, lightweight generation at one end, and then you connect them with glass fibers. And there are tremendous applications of these materials, the mixed 3,5s, like indium gallium arsenide phosphide and indium gallium arsenide, and they are tremendous applications. And I usually ask my students, have you heard of light waves? Only few people know about it. They use it every day. When you're making a call, you don't know on what mode the call is being sent. And now, and what I am going to address the issue is that mixed 3,5 layers, the atoms are not distributed at random. And I explain the next slide, what do I mean. I'll cover the phase separation in these atomic ordering, and then go to the mixed nitrides. And I'm going to finally show you these microstructures, which is the domain of material science and engineering, have a tremendous influence on the reliability of the devices, light emitting as well as the field effect transistors, and then give you summary and conclusion. Now, as an introduction, most of you have seen these structures. The mixed 3,5 layers crystallize in the zinc blende structure, which consists of two interpenetrating phase-centered cubics. Group 3 atoms reside on one sublattice, and the group 5 atoms reside on the second sublattice. These two sublattices are displaced from each other by quarter 111 in the 111 direction. So this is the structure. And as I said, I'll cover phase separation and atomic ordering. The issue is, when you make an alloy or mix two binaries to make ternaries and quaternaries to create materials with different band gaps, what happens to the distribution of species on the two sublattices? Rewording my statement is, suppose I want to grow indium gallium phosphide. I have indium and gallium on the sublattice of group 3. Are these species randomly distributed or something else goes on? And I will show you they are not. Of course, if they were randomly, I won't be here consuming one of your hours. And so they are not randomly, and they phase separate, and they atomically order, and they produce structures which no growth technique could produce. MBE, nanolithography, nothing can do that. Nature does it, and that's why I labeled it as self-assemble. Self-assembly to the metallurgists has been known forever. You take aluminum copper, you form aluminum, copper-rich precipitates in aluminum alloys. And what has happened is has been fashioned into science by the word self-assemble. And we material scientists have known self-assembly for a long time. Now, just to give you the background, what is phase separation? Phase separation is you have a solid solution, and that composition free energy diagram has inflection points, and you cool that material. It doesn't get to these end members, but the solution decomposes into A-rich region and B-rich regions. That's what we refer to phase separation in material science. It's in physics or material science. That's just introduction to the issue of phase separation. Now, the next is you're going to look at how does phase separation manifest itself in the materials. You are looking at an indium gallium arsenide phosphide layers grown by liquid phase epitaxy. What do you see? And the growth was on 001 plane of indium phosphide. The composition that we used, we grew the materials ourselves, emits at 1.33 micrometer. That's the wavelength used by the lightweight communication systems. You look in the plan view, you image with the 2:2 reflection, what you see is the speckle structure on a very, very fine scale. And the speckle structure has a wavelength. I'll tell you how we determine the wavelength, about 8 nanometer. Very, very fine scale structure. And then you see these coarse modulations You look at the same material with a reflection that is parallel to the growth direction. You don't see any contrast very similar to that one. What is suggesting phase separation is two-dimensional in nature. It doesn't occur along the growth direction, but it occurs along there is an operating reflection, but it occurs along the soft direction lying in the growth plane. If you have this arrangement, those directions happens to be 110 type. So what you conclude from these two micrographs, we have fine scale speckle structure, wavelength we can determine. I'll show you in the next slide how we do it, and there is no phase separation along the growth direction. And you may ask, what is this dark contrast due to? When phase separation occurs, you produce biaxial strains at the interface, and that buckles your layer, the surface of the layer, and this dark contrast is due to that. Now, the next slide will show you how you determine the wavelength. This is the electron diffraction pattern from the 001 position, and what you see is when you enlarge these two O spots, it is not circular. It has satellites, intensity around the Bragg position. And from the position of the satellite with respect to the Bragg spot, you can determine the wavelength. That Lipson did it in 49 in a Procroy-Salk paper, so you can apply the idea. So when phase separation occurs, you produce satellite intensity, and why you do that is the indium-rich regions have a larger lattice parameter than the gallium-rich regions, and that I'll demonstrate in the next slide or argue in the next slide. So there is phase separation in these materials, and summing it up, phase separation occurs and is two-dimensional in nature in this indium-gallium quaternary layers, occurs along the soft directions lying in the plane. There is no phase separation along the growth direction. And the wavelength that you see is out of the order of, I will say, 8 nanometer, the structure that is produced. Now, why does it occur? There are strain-related reasons. This is stable due to Pauling. You look at the tetrahedral covalent radius of gallium and look at the covalent radius of indium. Indium atom has a much larger covalent radius than the gallium atom. Materials, these atoms are tetrahedrally coordinated in the zinc plane structure. Group 5 atom is connected to 4 group 3 atoms, and the bond length that you have depends on the tetrahedral radii of the material. So indium to group 5 and gallium to group 5 bond lengths are different in the tetrahedron or tetrahedra. As a result, there is a tremendous strain in the material. So what the material does is phase separate. To avoid that, you can use the thermodynamic argument, but we use this argument to explain why phase separation occurs. Now, this is schematic illustration. What goes on the material, you are looking at the cross-section of the zinc blende lattice along the 110 plane. These are the first layer is the group 5 atoms, right? And the second layer is the third layer, you can look at group 3 atoms. Now, when you grow on this layer, you grow a bilayer. You grow a group 5 and group 3 together. You have to grow for the stability of the structure. The first layer is group 5. You will attach group 3 layer here, and the atoms will phase separate, go into that position. Then if I have arsenic, you get group 5 layer, and the whole process goes on. So recapitulating what I showed you here, that if you have size differences between the species occupying a certain sublattice, in 3-5, the material is going to phase separate. There are no violations of that idea. In the case of indium gallium phosphide, same thing happens. Indium and the gallium phase separate for the same reason I described, and indium gallium arsenide does the same thing, and which I will show you. And phase separation occurs along the soft directions lying in the growth plane. Is the reduction in strain energy that is the driving force for the occurrence of phase separation. Phase separation produces two-dimensional strains in the layer or two-dimensional biaxial stresses that causes buckling and give you the dark bands I showed you. Now, people used to argue that LPE phase separation occurs because it's an equilibrium. LPE means liquid phase epitaxy, because it's an equilibrium technique. We had to prove that point that it's not true. And it is, we then did the growth, MB growth of indium gallium arsenide on indium phosphide at different temperatures. This is the reflections we are using. That is 400, 450, and 500. And you see the speckle structure in all of these layers. And we can determine the wavelength from, again, the position of the satellites. And those results we can explain. But let me first give you the development, how the wavelength develops, how the amplitude develops in these materials. You can write a simple expression. The wavelength modulation wavelength is related to some constants. A, surface diffusion coefficient, and T is the time we take to deposit a bilayer. Once the bilayer is deposited, the diffusion of atoms cannot occur. This is the assumption we made. And you go for activation energy or self-diffusion, growth temperature, A and B are constants. So we measured the wavelengths of modulation from the diffraction patterns, then correlated with the, and the fit is fair, not bad. What it is telling you, we can measure the activation energy from it is 0.25 eV, and that correlates the migration of arsenic on the surface of these layers. So we can correlate that. Now, does phase separate? The question, interesting question is, you can keep studying physical metallurgy, you can study on semiconductor, but does it have an effect on properties? We measured the carrier mobility in indium gallium arsenide, but you have to, how did we do this experiment? We grew indium gallium arsenide of the same composition at different growth temperatures. And if you recall the phase separation concept I introduced, the higher the growth temperature, the composition difference between the end members is smaller. So if you measure the carrier mobility at, I say, room temperature, and you see this dependence, the higher the growth temperature you have of your indium gallium arsenide layers, the effect on the mobility is smaller. And if you measure this at 77, you see this mobility goes up, right? This mobility is lower, but the mobility goes up as you are growing at a higher temperature. Going back to the concept of phase separation and looking at the composition of the end members, you can rationalize. This is what we did. Indium-rich regions have a lower band gap. That's people have demonstrated it's acceptable. And the gallium-rich regions have a higher band gap. In equilibrium, the carriers would like to stay in the low band gap regions. When you apply a field to measure mobility, the carriers have to overcome the barrier between the low band gap region and the high band gap, micro barriers. And that's how we explain a reduction in carrier mobility in the presence of phase separation. Now, how does the phase separation affect the width of the photoluminescence peak? And that's what we did and shown here, just the opposite. Now you have indium-rich regions and gallium-rich regions in indium gallium phosphide. So indium-rich regions have a lower band gap, gallium-rich regions have higher band gap. So when you measure photoluminescence, the peak width changes, the full width half maximum width changes dependent on the growth temperature. And that's what we tried to show you here, that when you are growing at high temperature, the differences in composition between the two regions is much smaller, as the width will be smaller, whereas you grow at low temperature, width is larger. So this whole picture is internally consistent, that the occurrence of phase separation affects both optical properties and electronic properties of the layers. Life is not simple. In the same materials, what you observe is this is an indium phosphide, indium gallium arsenide phosphide, and indium phosphide heterostructure, which we grew by vapor phase epitaxy. The speckle structure is typical of the phase separation, and you have a 110 section. But in addition, what you see is the spots at half 111 position. So what you see is it is occurring, the periodicity along the 111 direction gets doubled as a result of ordering. So there is ordering coexisting with phase separation in these layers. Now I'll explain later how ordering comes in, but you see these spots, two sets of spots due to ordering. Ordering occurs on 2 of the 4111 planes. I don't think I have time to illustrate or explain why only or 2, but I'll show you the ordered structure we have. This is a 110 section again, as this is the growth direction. This is the coming out is a 110, this bar 1 bar 10. And the arrangement of the 111 planes in the zinc blende lattice is AA, BB, CC, just like the FCC lattice, but now you have 2 interpenetrating sublattices. You get AA, BB, and this structure. Now, this becomes a gallium-rich layer. Then the next one is your group 3, 5. Then the next layer is indium-rich layer, and this repeats. And if you look at the periodicity along this direction for this case, you will see it is double. So ordering occurs on the 111 plane, only 2 of the 4 111 planes. Now, how does the ordering occur? Mechanistically, the same argument, the size difference, helps you to understand that one. This is a section, cross-section along the 110 plane, and this you have seen it earlier. Now, when you have these exposed arsenic atoms on the surface, group 5 atoms, as I said, there are a lot of dangling bonds on the surface. So to lower the electronic energy of the system, you form dimers, as shown here. And we have done valence force field calculation to illustrate. Underneath the dimers, the arsenic bonds to arsenic to form a double bond, there is a compressive region, stress region. In between the dimers, you have tension region. And there is a compressive region and the tension region. Now, indium is much larger atom than the gallium atom. So what will happen is the gallium atoms will tend to segregate along this one more direction going into the plane. Indium regions will segregate along this direction. And of course, we don't observe experimentally, but the net effect is that when you do that and you grow the layer, you will see that you will produce the order, what is called the copper platinum order, by the occurrence of this. I guess I should have gotten rid of it. It finally woke up. So it is stress-induced ordering. All material scientists familiar with it, the segregation of impurities and edge dislocation, compression region and the tension region. And you can apply the same ideas and you will get this one. And if I take you to the next slide, why it is not moving? All right. So ordering occurs on the 111 planes, and it is stress-induced ordering because of the surface reconstruction. And the site difference is needed to selectively put atoms in certain sites. Our conjecture is phase separation occurs first, and then there is a movement of atoms very short distances to produce ordered structure. We never get order parameter of 1. The best we could do was 0.5 because it's time is too short to convert the phase separated structure into the ordered structure, and that's what we observe. Now, does ordering have an influence on the electronic optical properties? What we are looking, this is not our work. This is Japanese work, Gomyo and Suzuki from NTT. They grew gallium indium phosphide by liquid phase epitaxy, which is, there is no reconstruction in the case of LPE. Then they grew gallium indium phosphide by MOCVD, 3:5:3 ratio is this one, but they changed the growth temperature. What they observed is at a low temperature growth, the band gap doesn't change very much. As you lower the increase the growth temperature, you reach a minimum in the band gap, and then grow high temperature, then again goes back. The idea is here the temperature is too low to reorder the atoms. There is an optimal value where you can get the maximum order, and then when you grow at higher temperature, you get defective order. So phase separation changes, not phase separation, atomic ordering lowers the band gap of material. There is a story, Philips used to make these lasers for disc players, and they did not understand the growth, the atomic ordering very sensitive, or the band gap is very sensitive to atomic ordering. So they used to get fluctuations in the lasers that they were developing. So finally what they did, they went away from the exact orientation and killed atomic ordering, and they were able to produce lasers with a consistent wavelength. Now, you can also produce triple period superlattices in these materials by changing the reconstruction. Earlier one I was talking about 2x4, but you change the reconstruction to 4x2. Reconstruction, you know, it's we don't learn much in material science, but applied physics, they play a major role. But it's a simple concept. The atoms on the surface behave differently from atoms in the bulk. So you have a you can produce these reconstructions by changing 3:5 ratios in your growth system. And what you find is now you have two you have a triple period superlattice. This is the Bragg spot, superlattice spot back to Bragg spot. So the period now is a triple period instead of the double in the earlier case, and that's what is shown here. And the streaking of the superlattice spot is due to the imperfection in your ordered structure. They are very thin platelets. It's not a very good ordered structure, and that's what due to. Now, how do you explain the evolution of this ordered structure is shown here. When you have 4x2 reconstruction, this is the structure that you should focus on. You have reconstruction that produces a compressive stress. This is tensile stress, compressive stress, and tensile stress. So in the earlier case was compression, tension, compression, tension. Now you have compression, tension, tension, compression, and changes the order structure, and that's what is shown here. So we can explain why these order structures occur related to the stresses induced by surface reconstruction. 2 by 4 leads to a double period superlattice, and 4 by 2 leads to a triple period, but you have to have size difference in the atomic species of your materials. Now, shifting gear, coming to the group 3 nitride materials, and you will see conceptually they are very similar. Crystal structure is different. Now these materials crystallize in the woodcitic structure, and that's what I've tried to show you. And the nitrogen, you can choose blue or yellow color. These are group 3 atoms, and these are group 5 atoms. What is the difference between woodcitic and the diamond cubic? The sublattices are made up of SCP units. So they consist of 2 SCP units shifted just like in the case of diamond cubic. And of course, group 3 atoms reside on one sublattice, and group 5 nitrogen is the one. Why these are important? The blue DVDs you have, they are made out of blue lasers based on such materials. And of course, the limit is the application are very unlimited for this material. Always to give challenge to our students, if I tell them, if they can dope aluminum nitride p-time, they can produce electronic devices which will work at 1,000 degrees centigrade, 1,000 degrees. You can monitor the jet engines, you can monitor the oil wells, you can monitor the blast furnaces, anything you want to monitor. And the silicon devices at the moment can go only to 120. The reason is thermal noise kills the device. But since the band gap is very large, you can make them. And these potentials haven't been explored. They are now these blue DVDs, lasers, or LEDs that you see are based on indium gallium nitride. And you can change the composition of indium, and it will change the emission wavelength. When you are below a certain value and look at 3% of indium, what you see is your spots, the diffraction spots are spherical. You go to 12%, 22 in this case, spots are no longer spherical, and they have satellites. And as I said earlier, from the position of the satellites, you can determine the wavelength of the modulation in these materials. We have done over a range of composition these studies. Luckily, we have a growth system ourselves. Otherwise, it's very difficult to do these studies. When I joined ASU in '97, I made sure we had a growth system to ourselves in the materials program or materials department. And when you grow, have a small fraction of indium, the wavelength along these directions, that's along which direction the phase separation occurs, is infinity. Means there is no phase separation. What increase the composition and you look at it, the wavelength decreases as the indium content increases, and that's the formula we use to determine the wavelength. And the reason is the driving force for phase separation will increase as you increase the indium content in your layer, and that's what is illustrated here. And also I should point out, we are growing these layer on 0001 is the basal plane of the woodcitic structure, which is equivalent to a 111 plane of the zinc blende structure. What do you see in the microstructures? 3%, if you have a standard, those who are familiar with the microstructure, there are no modulations present in this structure. But look at in this case, it's 12%. You see speckle structure, you see the stripe structure, and you see the boundaries. So there are 3 features I need to explain. What the stripe structure is, what the speckle structure is, why do you have the boundary? So when you grow on 001, what we showed is the phase separation occurs along 1 bar 100 or 112 bar O direction. There are 3 directions of each in the basal plane. If phase separation occurs along one direction and then neighboring regions that occur along another vector, you will produce the boundaries. We don't fully understand the structure of these boundaries, but we can rationalize. This is speckle structure, which I said is due to phase separation. And what is the correlation with this one and this phase separation? I'll try to illustrate in the next slide. This layer was grown at a much higher growth rate. There was a reason why we did that. We will try to understand why they are ordered. And you see the dark stripes are indium-rich. We haven't proven. Dark stripes are indium-rich regions and the light stripes are gallium-rich regions. And if you look at it, the volume fraction fits very well. And also look at the crystallography. The directions normal to these stripes tend to lie along one of these directions. So, width of, say, this is Alex 100 nanometers, so it must be 10 nanometers. Very, very narrow. What's the correlation between the speckle structure shown here, stripe structure shown here? Our hypothesis is the stripes form first when the material phase separates, and then it decomposes into the speckle structure. This is just a hypothesis. We have not proven that's true. This is a structure we were not trying to grow, but we were trying to study phase separation in aluminum gallium nitride. And what you get is a vertical alignment of the phase separation, vertical modulations. And the way it is, dark contra change, this is the light region, the indium gallium rich, and the dark regions are the aluminum rich. And they line up in the vertical direction. We were puzzled why this happens in these materials. You can see when I give you an explanation why this happens is by manipulating the growth conditions, I would be able to change the period along these directions and the extent of these modulations is shown here. You start growing aluminum gallium nitride on aluminum nitride sapphire. This is a sapphire substrate. This is the buffer layer you grow on it. And we showed that these layers phase separate. The aluminum-rich regions wet the underlying aluminum nitride, but the gallium-rich regions don't wet. And that's, I think, that's what is illustrated. Their structure is shown here. This is. You now deposit on these. There is asymmetry in wetting behavior. A on B or B on A, and you see this wets this one, you get this structure, and you start growing. And this is, when you remove the interface between A-rich regions, this dashed here, you can explain the evolution of the structure. I can change the modulations here by changing my growth conditions and composition, and then you can see the extent of the aluminum-rich regions and the gallium-rich regions in the modulated structure. We have not measured the electronic properties. Along the growth direction and parallel to the normal to the growth direction, that's a challenging problem to have. So this one MBE. Yeah, LPE of aluminum alloys are very difficult, as you know. This is MBE. And why does if you go back in history, aluminum gallium arsenide doesn't phase separate. But aluminum behaves 2% smaller than gallium in the case of nitride. I'm not going to present any explanation when Alex is sitting here why that happens. But this is a fact. Aluminum nitride lattice parameter is smaller than gallium nitride. So aluminum is behaving differently in the nitrides than it does in the arsenide. And that leads to phase separation, the 2% size difference. You don't see phase separation in aluminum gallium arsenide. There are examples given, but they are unreliable. Now, just like the 3,5, the nitrides also order. And the ordering is you get extra spot at the 001 position. In the woodstatic structure, in the diffraction pattern, you should not see 001 spot. And you see them and in indium gallium nitride. Again, the periodicity along the growth direction gets doubled as a result of ordering. In these materials, you see, and the intensity depends on the growth rate, and the conclusion, I think I can't develop on that because of time constraint. You see the same thing in aluminum gallium nitride. You get spots and diffuse intensity along the 001 spot. You see that. You get the ordering on that in those. Now, what's the mechanism? I will preface my remarks, we don't understand. And I'm going to speculate on the base of the model Northrop developed. This is the arrangement of plausible arrangement of atoms in a random alloy. What happens in the ordered alloy is you get gallium, nitrogen, indium, nitrogen, gallium, and the periodicity gets doubled. And why does it do that? According to Northrop, if you look at the 10 facets as shown here, they are preferred sites for the attachment of B2 or the preferred site for the attachment of gallium atoms, and the T1 site is for preferred site for the attachment of indium atoms. There are reasons for it. You can see that it can continue. And is there evidence? Some evidence we have, but it is not clear-cut that indeed that happens. And that's the issue is there, phase separation and atomic ordering do occur, but we don't fully understand the mechanism by which ordering occurs in these materials. Now, our president calls this use-inspired research. I call it relevant basic research. All these, do they have relevance to real devices or not? What you are looking at is those people who are my vintage are familiar with dark line defects in gallium arsenide based lasers. If you look at the active region of the device, you don't see these dark regions. This is 70 to 73 time frame. But with the operation of the laser, you develop these dark lines. They don't worry about the dark spot defects that's shown here, that due to the indiffusion of metal into the layers, but these are the important ones, the dark line. What happens is the device dies. They develop these dark lines into the structure, into the active layer of the device, and it dies. Now look at those dark lines, and what you see is those who do dislocation theory will be enamored. This is dislocation in the layer. It multiplies, highly crinkled, showing that climb is occurring in these materials, in the development of the dark line defects. And this is another dislocation multipliers. Already tells you if you want to make reliable lasers, you better reduce the dislocation density to minimum in your material. Now the structure, these are the dipole structures. How do they evolve? And we had argued, and other people had argued, that it's a tongue twister what I'm going to say, non-radiative recombination enhanced glide and climb. When electron-hole pairs combine very close to the dislocation, it doesn't emit a light photon. Photons don't come out, but that energy gets coupled to the dislocation. In the presence of stress, the dislocations climb and glide. That is the non-radiative. Very interesting work one can do. When you creep these materials and you shine light simultaneously, do you see all these effects? There was some evidence in cat telluride that you do. And now, those who study mechanical properties, if you have phase separation, right, dislocations are not going to move. You can argue which model, but the shear moduli of the two regions, indium-rich regions and gallium-rich, are going to different. So the presence of phase separation will retard the multiplication of dislocation. And next few slides I'll argue the presence of ordering will retard the climb of dislocation. So what you have, if you take the extra half plane of an edge dislocation in indium gallium arsenide, this is ordered. You see the dislocation terminates along the nitrogen, Mn terminates in the group 5 according to that. Now if you want to preserve the order in the material, the atoms have to come in a certain way, reach the dislocation core in a certain way. This has to come, this was indium, let's say indium, and then arsenic. You can't put gallium or you can't put nitrates in there. And obviously you can see, being a statistical process, you can't do that. So the presence of order in the material will retard the climb of dislocation. The presence of phase separation will retard the multiplication of dislocation. So what it tells you, if you are worried about, if you are dealing with light emitting devices which degrade by the multiplication of dislocation, these things can't happen easily. You will prolong the life of your devices. And that's what you observe. Indium gallium arsenide phosphide on indium phosphide, even though it's more defective, is phase separated. It has a much longer life than the gallium arsenide based devices, which are more perfect because they are not phase separated. Now suppose I want to make a field effect transistor based on the indium gallium arsenide layer. It phase separates, it reduces the mobility. So you can make much faster devices if you can prevent the phase separation. What certainly I have tried to argue, or not so certainly, that you have to tailor the microstructure of your active layer to get the right conditions for your device. And this is, I think those who deal with structure property relations, mechanical properties, you tailor the microstructure to get certain properties. You tailor the microstructure to get magnetic property. You tailor the microstructure to get superconducting. What I have shown you here, you must tailor your microstructure to get the optimal behavior of a device. Doesn't apply to a binary or a silicon germanium because they contain only one type of atoms. But in the case of compound semiconductors, the nitrides, the microstructure of the mixed layers become very important. And their coupling between the materials people and the electronics or solid state materials becomes very important. And with my summary, what I showed you is when you have atomic species which differ in their tetrahedroradii and you make a ternary out of a binary, you are going to phase separate your material. And you are also going to atomically order your material. And two types of phase separation. And also argued that these two features, microstructural features, affect the electronic properties of your material. And then, and I believe this conclusion, probably for the first time anybody has argued that you must tailor the microstructure of a layer. You can't treat a layer as a black box. You need to understand what is in it, and you can get optimal performance by tailoring those. Thank you very much for your attention.
Any questions? Time for a question or two?
Yeah. Great.
That's a great talk. Thank you very much. And I have a question about this electronic properties and this, related to this phase separation. Can you explain that actually based on the mobility change when the electron crosses the for example, gallium-rich and poor phases and band gap changes and all that.
Yeah.
But I wasn't quite sure it can be explained by only mobility, because I suspect that at the interface between poor and rich, there must be bending.
Oh, yeah. What I said, you have interfaces, and there are micro interfaces, and yeah, no.
More or less, I mean, concentration effect has to be taken into account as well.
The band gap argument takes care of the concentration effect. Yeah, we did.
Okay, all right.
That was not our original. There was an article 1984 in Physical Review B, blood is blood than somebody else, where they argued you get compositional differences, you get and then different band gaps, and then you have create a heteroband, hetero interfaces. Yeah.
So the mobility degradation is a scattering effect from that variation of potential of the different regions?
Yeah. You can call scattering effects. I call these heterobands, and you have to cross them to move the carriers from one region to the other, the next one, to get to the end. Yeah.
Typically, how large is the variation in
Composition. There is only one measurement done at Oxford. They have atom probe. And they did work on indium gallium arsenide, plus minus 7% between indium rich region and the gallium rich. We are now working with them on the nitrides, what composition differences we are getting. Yeah. And what is, I didn't pose that question, is I argued that it's two-dimensional, right? How do they stack up in the vertical direction, the layers? And hopefully that answer will come when we do three-dimensional atom probe. The microscopy can't give you that answer. Atom probe is becoming very powerful technique. We would like to acquire one of those at ASU because we have 12 microscopes, but we don't have a single atom probe. The next faculty line should go to the atom probe.
It's amazing, Subhash, that at your scale discussion, that the fact that the dislocation line will be limited by phase separation, and dislocation line will be limited by ordering. Still continue.
Oh, I mean, there's no direct evidence. These are the arguments I have developed to explain.
It makes sense because
Yeah.
the size selectivity of the time process will be taught because of the specificity
Yeah.
of the positions
Yeah.
required.
If you don't do that, you introduce domain boundaries, right?
Yes.
Climb induce domain boundaries. It is, as I call my love affair with the semiconductors for the last I learned a lot as I was going through. And I could bring what I learned in material science to the semiconductor science in terms of dislocation effects.
I think your interaction with Jack Christian was the transition between deformation to this stuff. He was into both.
No, actually, Bell Labs forced it on us. As I said, semiconductors, Subhash, that's where the action is.
Have you looked at silicon germanium?
You get orders? You do. I didn't, but IBM did. Yeah, same order structure, copper platinum. Francois Lagousse's work. Yeah, the same ordered structure you see.
Thank you very much. Very impressive.